Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know, where in the world are you listening from? Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into Earth's first great transformation, the moment our planet learned to breathe poison and call it oxygen. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. The ocean is green. Not the blue-green of modern seas, not the turquoise of tropical shallows, but a deep, opaque green that swallows light within meters of the surface. This is water thick with dissolved iron, with methane, with the bodies of bacteria so numerous they form a living haze. The year is approximately 2.4 billion years before the present, and the Earth's oceans are a bacterial soup that has remained essentially unchanged for over 1 billion years. The sky above is pale orange, almost salmon-colored in certain lights, thick with methane that catches the sun and holds its warmth close to the surface. There are no clouds as we would recognize them. There is no ozone layer. Ultraviolet radiation pours down onto shallow seas and coastal rocks with an intensity that would sterilize any modern organism within hours. But life exists here. It thrives. In fact, in forms so alien to our experience that they would seem more at home in a chemist's nightmare than in any ocean we might imagine. Single-celled organisms cluster in mats along the sea floor, building slow limestone domes called stromatolites that rise like mineral mushrooms from the sediment. These structures grow at the pace of stone, millimeters per year, perhaps a few centimeters in a good decade. And yet, they represent some of the most successful architecture in Earth's history. Some of these domes will stand for hundreds of millions of years, recording in their layers the slow chemical transformation of a planet. Among the bacteria coating these structures, a particular lineage has stumbled upon something revolutionary. Though revolution is far too dramatic a word for a process that unfolds over geological time, these are cyanobacteria, and they have learned to split water molecules using sunlight, releasing oxygen as waste. It is not an efficient process. It is not even, initially, a particularly successful one. Oxygen is violently reactive, combining almost immediately with whatever it touches: iron, sulfur, organic matter, the very cells that produced it, for hundreds of millions of years. Every oxygen molecule produced by these bacteria finds something to oxidize within moments of its creation. The oxygen never accumulates. It simply rusts things, quietly and without pause. The ocean floor is beginning to change color. In shallow basins, where cyanobacterial mats grow thickest, the sediment takes on a reddish hue. Iron that has sat dissolved in seawater for eons meets oxygen and falls out of solution, becoming iron oxide, rust, essentially, that drifts down like bloody snow to settle on the bottom. This process will continue, in fits and starts, for the next several 100 million years. It will create some of the largest iron ore deposits on Earth, the banded iron formations that modern humans will mine for steel, pulling ancient rust from the ground to build cities and ships and bridges. But that is still 2.5 billion years away. For now, there is only the slow precipitation of iron, the gradual clearing of the seas, the patient work of bacteria that have no concept of the transformation they are engineering. The oxygen they produce is toxic. This cannot be overstated. To the vast majority of life on Earth at this moment, oxygen is a poison as deadly as cyanide is to us. It strips electrons from cellular machinery, shreds delicate organic molecules, creates reactive oxygen species that cascade through living tissue like microscopic wildfires. The anaerobic organisms that have dominated Earth's oceans since life's origin, the methanogens, the sulfur reducers, the hydrogen breathers, all of them are slowly being poisoned by this new waste product. They retreat to deeper waters, to oxygen-free sediments, to any niche where they can escape the rising tide of this corrosive gas. Many lineages will go extinct, others will persist in increasingly marginal environments, refugees from their own planet's changing chemistry. Only took 1 billion years to perfect photosynthesis, and another few 100 million to start actually changing anything. The cyanobacteria go about their work with the urgency of stone. There is no acceleration, no sudden bloom, just the steady accumulation of these organisms in shallow sunlit waters, and the steady production of oxygen that immediately combines with iron. The oceans are a chemical buffer of staggering capacity. Every drop of seawater contains dissolved iron waiting to rust, and there are oceans upon oceans of it. The oxygen doesn't stand a chance of reaching the atmosphere. Not yet. First, it must rust every bit of iron in the sea. This will take, by conservative estimates, another 300 million years. In certain light, the stromatolites look almost artistic, their domed surfaces catching the low-angle sun in patterns of shadow and mineral grain. They grow in shallow tidal zones where the water is warm and the light is strong, places where modern coral reefs might thrive. But there are no corals, no fish, no seaweed or sea stars or anything that moves on its own. Just these bacterial cities, these living stones, and the patient chemical work they perform. Photosynthesis proceeds. Oxygen bubbles form on the surface of the mats, each one a tiny sphere of poison that rises briefly before dissolving into the water, finding iron, becoming rust. The process is so slow that any individual bacterium would perceive no change from one generation to the next. Lineages rise and fall. Mutations accumulate. Entire species come and go. And still the ocean remains green. The iron remains dissolved. The oxygen remains captured in stone. The mystery that scientists still debate is the timing. Why does the great oxygenation event begin when it does? Cyanobacteria have been producing oxygen for hundreds of millions of years before this moment. What changes? Is it the volume of oxygen production, a slow crescendo reaching some critical threshold? Is it the exhaustion of the ocean's iron reserves, the gradual saturation of that enormous chemical buffer? Or is it something else entirely? A shift in tectonic activity, perhaps, or changes in volcanic outgassing that alter the balance between oxygen production and oxygen consumption? The rock record preserves the what, but obscures the why. We know that oxygen rises. We can measure when it happens, see it written in isotope ratios and mineral assemblages, but the trigger remains uncertain, a gap in the story that invites speculation. What is certain is that the process has begun. The first breath of iron, the first rust, the first clearing of those ancient green seas. Oxygen accumulates in the sediment, locked into minerals, building the banded iron formations layer by microscopic layer. The bacteria continue their work, indifferent to consequence, prisoners of their own chemistry. And somewhere in the depths of these Archean oceans, something is about to shift. The buffer is filling, the iron is rusting, and eventually, not soon, but eventually, there will be nowhere left for the oxygen to go but up. The oxygen pools in the shallows first, in tide pools and lagoons where evaporation concentrates the water, where cyanobacterial mats grow thickest and photosynthesis runs most intensely during the long Archean days. The local iron supply begins to exhaust itself. These are small pockets, isolated systems where the balance tips slightly, for a few hours each day, when the sun is strongest and the mats are most active. Free oxygen actually persists in the water column. Not much, a few parts per million, perhaps barely detectable by modern standards, but it is there, unbound, corrosive, looking for something to oxidize. The bacteria producing this oxygen are, in a sense, poisoning themselves. They have no mechanism to deal with reactive oxygen species, no catalase or superoxide dismutase to neutralize the damage. They simply outproduce the problem, generating so much oxygen during daylight hours that the percentage that damages their own cells becomes statistically manageable. It is a brute force solution, and it works only because these organisms reproduce so quickly that cell death is merely overhead, a cost of doing business in a photosynthetic economy. By nightfall, any free oxygen has combined with something, organic matter, reduced minerals, the cells of less tolerant organisms nearby. The water returns to an anoxic state. The cycle repeats with the sunrise. This daily rhythm will continue for tens of millions of years. Oxygen rises with the light, disappears with the dark, never accumulating beyond the local scale. The open ocean remains green and iron-rich, a vast reservoir that swallows any oxygen that escapes the shallows. Currents carry oxygen-poor water into the lagoons, mixing with oxygen-rich surface layers, creating chemical gradients that shift with tides and seasons. The stromatolites record these fluctuations in their growth patterns, laminae of light and dark stone, each representing a different chemical state, a different balance between oxygen production and iron precipitation. Reading these patterns is like reading tree rings, except each ring represents not a year, but perhaps a decade, and the tree is made of limestone and bacterial slime. The organisms dying in these oxygen-rich zones leave no obvious fossil record. They are anaerobes, mostly, methane producers and sulfur breathers who find themselves on the wrong side of chemistry. Some may adapt, retreating to deeper layers within the microbial mat where oxygen doesn't penetrate. Others simply vanish, their lineages ending in a place and time that will leave no trace beyond a slight change in the isotopic signature of the rock. Extinction at this scale is invisible. There are no bones, no shells, nothing but the absence of certain metabolic signatures in the chemical record. Life loses diversity in these shallow zones, becoming dominated by the organisms that can tolerate, if not thrive in, the presence of oxygen. Only took a few 100 million years of daily poisoning to get used to the taste. The cyanobacteria themselves show no obvious signs of stress. They continue building their stromatolites, layering stone upon stone, growing in the same patient rhythm they have maintained since their evolution. The oxygen crisis, if it can be called that, is entirely a problem for other organisms. The producers of the poison are, themselves, mostly immune. They live at the surface of the mats where oxygen concentrations are highest, where the light is best, where competition from oxygen-intolerant bacteria has been eliminated. In a sense, they are terraforming their own microenvironment, creating conditions that favor their own survival at the expense of everything else. It is not intentional. Of course, it is simply chemistry, following its gradient. The atmosphere above these shallow seas remains virtually unchanged. The oxygen produced during the day escapes into water, not air. Even if some molecules do make it to the surface and bubble out, the atmosphere itself is a chemical trap. Methane, hydrogen, reduced volcanic gases, all of these react with oxygen on contact. The sky is still pale orange. The ultraviolet radiation still pours down. Nothing about the world above suggests that anything is changing below. A time traveler standing on an Archean shoreline would notice no difference between this era and 100 million years earlier. The transformation is entirely submarine, entirely chemical, entirely slow. But the iron is rusting. In coastal basins and shallow continental shelves, the sediment is turning red. Layers of hematite and magnetite accumulate, separated by thin bands of silica-rich chert, creating the distinctive banded appearance that will give these formations their name. The banding represents cycles, seasonal, perhaps, or linked to longer climate variations. times when iron precipitation was intense and times when it slowed. Each band is a chapter in the story of oxygen's rise, a visible record of the moment when the ocean's chemistry began to tip. These rocks will endure for billions of years, some of the oldest sedimentary formations on Earth, waiting to tell their story to organisms that won't evolve for another 2 billion years. The open ocean is a different world, miles from shore, in the deep basins where light doesn't penetrate and cyanobacteria cannot survive. The water remains as it has always been, green with dissolved iron, rich in methane, populated by anaerobic bacteria living off chemical energy from hydrothermal vents and the slow decay of organic matter raining down from above. These deep ecosystems are insulated from the changes happening in the shallows. The oxygen never reaches them. Currents do eventually mix surface water down, but by the time it arrives, any oxygen it carried has long since reacted away. The depths remain an anaerobic refuge, a preserve of Earth's original chemistry. This refuge will persist, in various forms, for billions of years. Even in the modern ocean, there are anoxic basins, oxygen minimum zones, places where the ancient metabolisms still operate as they did in the Archean. The scientific uncertainty here is one of scale and timing. We know that oxygen begins accumulating in shallow environments before it reaches the deep sea or the atmosphere. We can see this in the rock record, oxidized minerals appearing first in near-shore deposits, spreading gradually to deeper settings. But how long does this shallow oxygenation persist before oxygen breaks through to the surface? Decades, millennia, millions of years. The resolution of our data is too coarse to say with certainty. We have snapshots separated by vast stretches of time, and we try to draw smooth curves between them, knowing that the real process was probably anything but smooth. There were likely oscillations, reversals, periods when oxygen production surged and periods when it crashed. The rocks show us the net trend but hide the variation. What we do know is that the poison is spreading, slowly, incrementally, in a pattern dictated by ocean circulation and biological productivity. Oxygen-rich water is expanding its territory. The boundary between oxygenated and anoxic zones shifts outward from the coasts, driven by the relentless production of oxygen in the shallows and the slow exhaustion of the ocean's iron buffer. It is a wave front moving at geological speed, invisible to any observer, measurable only by the patient analysis of rock chemistry 2.5 billion years later. The cyanobacteria photosynthesize, the iron rusts, the anaerobes retreat, and the oxygen waits, accumulating in pockets, testing the boundaries, preparing for the moment when there will be nowhere left to go but up. Above the green seas, the atmosphere holds a secret in plain sight: methane. That simplest of hydrocarbons fills the air in concentrations thousands of times higher than modern levels. It is produced by methanogens, anaerobic bacteria living in sediments and deep waters, organisms that breathe methane the way modern animals breathe oxygen. They release it as waste, and it bubbles upward, escaping from the ocean into the sky where it accumulates and persists. Methane is a powerful greenhouse gas, far more effective at trapping heat than carbon dioxide, and it keeps the young Earth warm despite the sun being perhaps 25 to 30% dimmer than it will be in the future. This is the faint young sun paradox, how Earth maintained liquid oceans under a cooler star. And methane is part of the answer. The sky's orange tint comes from methane haze, organic molecules created when ultraviolet light strikes methane in the upper atmosphere, breaking it apart and allowing the fragments to recombine into more complex hydrocarbons. These molecules scatter light differently than the nitrogen and oxygen that will someday dominate, giving the Archean sky its distinctive color. At sunset, the horizon glows amber and rust, colors that won't return to Earth's skies for billions of years. A human standing on an Archean beach, an impossible human. Of course, since oxygen-breathing animals cannot exist yet, would see a world painted in tones of orange, red, and brown, under a sun that feels weaker than it should, in air that would kill them within minutes. The methane ceiling is stable. It has been stable for over 1 billion years, maintained by the steady production of methanogens in the anoxic ocean and sediments. The biological pump operates in reverse from modern times. Instead of photosynthetic organisms pulling carbon dioxide from the air and producing oxygen, the dominant metabolisms pull hydrogen and carbon dioxide and produce methane. The result is an atmosphere that stays warm, that keeps the oceans liquid even under a faint sun, that allows life to continue its slow evolution in the greenhouse comfort of its own gases. There is no reason to think this will change. The system is in equilibrium, balance between production and destruction, and equilibrium can last for geological ages, except that oxygen is beginning to rise in the shallow seas. It doesn't reach the atmosphere yet. The water itself is still a chemical barrier, and any oxygen that does escape immediately reacts with methane or hydrogen or reduced gases from volcanic eruptions. But the potential is there, building in those oxygenated tide pools and coastal basins. Oxygen is methane's destroyer. When they meet in the presence of ultraviolet light or certain catalysts, they react to form carbon dioxide and water. The reaction is exothermic, energetic, fundamentally irreversible. Methane is a reduced molecule, full of chemical energy. Oxygen is desperate to oxidize something. They are thermodynamically incompatible, and one of them will eventually win. Only took Earth 1 billion years to build a greenhouse, and it's about to tear it down without noticing. The irony is profound in a way that would be amusing if there were anyone around to appreciate it. The same organisms that are producing oxygen in the shallows are benefiting from the warmth that methane provides. The cyanobacteria thrive in the warm Archean climate, growing prolifically in tropical and subtropical waters, producing more oxygen, which will eventually destroy the methane, which will cool the planet, which will create conditions far less favorable for the cyanobacteria themselves. It is an act of accidental self-sabotage that will take tens of millions of years to complete, and there is no mechanism by which it can be avoided. The bacteria have no foresight, no ability to regulate their impact on the global system. They simply do what their biochemistry dictates. The methanogens, meanwhile, continue their own work in the depths. They are unaware of the oxygen accumulating in distant shallow zones, insulated by miles of anoxic water from the changes happening at the surface. Their populations remain stable, their metabolic rates unchanged. They produce methane at the same rate they always have, releasing it into the water where it dissolves and eventually diffuses upward toward the atmosphere. The flux has not changed. What will change, slowly, incrementally, is the fate of that methane once it encounters oxygen. For now, the two gases occupy different worlds: methane in the atmosphere and deep water, oxygen in the shallow seas. But those worlds are approaching each other. The scientific question that remains partially unresolved is how quickly methane can be destroyed once oxygen reaches the atmosphere. The reaction requires either ultraviolet light or certain chemical intermediaries to proceed at significant rates. In the modern atmosphere, methane has a lifetime of about a decade before it oxidizes, but the modern atmosphere has vastly more oxygen and less methane. In the early Archean, with methane concentrations so high and oxygen concentrations initially very low, the kinetics might have been different. Some models suggest a long period, tens of millions of years, during which both gases coexist in the atmosphere, creating a complex chemistry that has no modern analog. Other models suggest a more rapid transition, a tipping point beyond which methane destruction accelerates and the greenhouse collapses relatively quickly. The rock record is ambiguous, and different research groups argue for different scenarios. What is certain is that the methane ceiling is doomed. It doesn't know this yet, if a chemical system can be said to know anything, but the process that will destroy it is already underway. The oxygen accumulating in shallow seas is the match waiting for fuel. The methane in the atmosphere is the fuel waiting for a match. Between them is a barrier of water and time, a buffer that is gradually being consumed. The iron in the ocean continues to rust, removing oxygen from the water, preventing it from reaching the air. But iron is finite. The ocean's buffer capacity, vast as it is not infinite. Eventually, not soon, but eventually, the rust will be complete, and the oxygen will have nowhere to go but up into the methane-rich sky. The stromatolites continue growing, layer by patient layer, in shallow seas warmed by the very greenhouse effect they are helping to undermine. The sunset continues to glow orange and amber, reflecting off water that is slowly, imperceptibly turning from green to something approaching clear as iron precipitates out. The methanogens continue breathing methane into the depths, sustaining the atmospheric reservoir that keeps the planet warm. Everything appears stable. Everything appears as it has been for 1 billion years. And beneath that appearance, the chemistry is shifting, tilting toward a transformation that will remake the planet's surface, freeze its oceans, and ultimately enable complexity beyond anything the Archean world can imagine. But that is still far ahead. For now, there is only the warm sky, the green sea, and the slow work of organisms who cannot conceive of the future they are building. The rust settles through green water in a rhythm older than days, each grain of iron oxide smaller than a blood cell, laden with oxygen that moments before was free, drifts downward through the water column, following gravity to the seafloor. The descent takes hours, sometimes days if the water is particularly still, and during that fall, the particles collide, aggregate, form small clusters that sink faster. By the time they reach the bottom, they have become a fine red powder that mantles the sediment like brick dust, like the residue of some submarine foundry. This powder will become stone. The water above will become clearer, and the process will repeat. Day after day, year after year, for millions of years, the banding begins as a seasonal signal. Most researchers believe, during times of high biological productivity, perhaps linked to variations in sunlight, nutrient upwelling, or ocean circulation, cyanobacterial activity surges. More photosynthesis means more oxygen, which means more iron precipitation. The red layers form during these productive periods, accumulating perhaps a few millimeters per year, building up until the season changes or the nutrient supply shifts. Then productivity drops, less oxygen is produced. The iron precipitation slows or stops entirely. Instead, silica-rich sediments, chert, microcrystalline quartz, settle to the bottom, forming pale gray or white layers between the red iron bands. The alternation creates stripes visible to the naked eye, a barcode written in minerals, each couplet of red and pale representing some cycle in the Earth's ancient climate or ocean chemistry. The resulting formations are among the most visually striking rocks on Earth. When cut and polished, banded iron formations reveal patterns that look almost deliberate, perfect parallel stripes of deep red hematite alternating with silvery gray chert, sometimes wavy from later deformation, sometimes perfectly flat as if painted. These rocks will cover vast areas of the continents, particularly in what will become Western Australia, South Africa, and the Lake Superior region of North America. They represent billions of tons of iron, enough to supply human industry for thousands of years, all precipitated from seawater by oxygen produced by bacteria that had no concept of metal or industry. The largest iron ore deposits on Earth are bacterial waste, frozen in stone. Only took the ocean a few 100 million years to rust out, one layer at a time. The accumulation rate seems impossibly slow from a human perspective, millimeters per year, perhaps a meter per millennium, but the process is relentless. There are no pauses, no reversals, just the steady rain of oxidized iron settling onto the seafloor wherever cyanobacteria produce oxygen. The formations grow thickest in shallow continental shelf environments where light penetration is good and biological productivity is high. In deeper basins, the banded iron formations are thinner or absent entirely because oxygen never reaches those depths in significant concentrations. The stratigraphy reveals the geography of ancient oxygen production, mapping out the zones where photosynthesis was most intense 2.5 billion years ago. The bacteria themselves leave almost no direct fossil record. Occasional stromatolitic textures, rare microfossils that might or might not be cyanobacteria. That's the extent of it. We infer their presence from the chemistry, from the isotopic signatures that indicate biological rather than purely geochemical processes. Carbon isotopes, in particular, tell the story. Photosynthesis preferentially incorporates the lighter isotope of carbon, carbon-12, into organic matter, leaving the heavier isotope, carbon-13, relatively enriched in the remaining dissolved carbon dioxide. This signature appears in carbonate minerals that precipitate from the same water where the iron is rusting, a chemical fingerprint of life's activity. We read the rocks and deduce the presence of vast bacterial populations, even though the bacteria themselves are long gone. The iron comes from hydrothermal vents and the weathering of the early continents. Volcanic activity on the seafloor pumps iron-rich fluids into the ocean, and rivers carry dissolved iron from the land. In the anoxic conditions that prevailed before the great oxygenation event, iron remains dissolved in water almost indefinitely. It is only when it meets oxygen that it precipitates. So the ocean becomes, in effect, a conveyor belt. Iron enters from below and from the continents, circulates through the water column, encounters oxygen in the shallow oxygenated zones, and falls out as rust. The system will continue until the rate of iron input can no longer keep up with the rate of oxygen production. That point is approaching, though it is still millions of years away. The mystery preserved in these formations is the question of periodicity. The bands are remarkably regular in some localities, suggesting a driving force with consistent timing. Is it seasonal variation in productivity, as most scientists suspect? Or could it be something else, perhaps variations in volcanic activity, changes in ocean circulation, or even astronomical cycles affecting Earth's climate? Some researchers have suggested that the banding might record Milankovitch cycles, those long-term orbital variations that drive ice ages in more recent Earth history. If true, it would mean we can read climate cycles from 2.5 billion years ago, encoded in the thickness and composition of rust layers. But the evidence is ambiguous, the preserved record incomplete. We see patterns but struggle to identify the clock. What is beyond dispute is that these formations represent an enormous chemical transformation. Every atom of iron in these rocks was once dissolved in seawater. Every molecule of oxygen locked into that iron was produced by a living organism. The mass balance is staggering. Estimates suggest that the oxygen required to precipitate all the Archean banded iron formations represents hundreds of millions of years of photosynthetic activity. It is a monument to bacterial metabolism, to the cumulative power of microscopic organisms operating across deep time, and it is also, in a sense, a chemical buffer being gradually consumed. The ocean is a finite reservoir of dissolved iron. It can absorb only so much oxygen before that reservoir is exhausted. The seafloor continues to accept its burden of rust. Red dust settles onto gray chert, which settles onto red dust, building formations that will eventually be hundreds, even thousands of meters thick. The cyanobacteria photosynthesize in the shallows, indifferent to the consequences. The oxygen they produce finds iron, becomes hematite, settles to the bottom. The process is so consistent that it creates some of the most laterally continuous rock formations in the geological record, banded iron formations that can be traced for hundreds of kilometers across ancient continental margins, maintaining the same thickness, the same banding pattern, the same chemistry. They are proof of a planet-wide process, of ocean atmosphere chemistry operating at a scale that dwarfs anything in more recent geological history. And they are also proof that the buffer is working, that the iron is capturing the oxygen, that the atmosphere remains unchanged. For now, the threshold arrives without announcement, somewhere in a shallow basin, on a continental shelf now long since destroyed by tectonic recycling. The last dissolved iron in the local water column encounters oxygen and falls out of solution. For the first time in Earth's history, there is no iron left to rust. The oxygen produced by cyanobacterial mats has nowhere to go. It begins to accumulate in the water, dissolved but unbound, chemically free. The concentration rises from parts per billion to parts per million. The water, in this small location, becomes saturated with oxygen. And still the cyanobacteria photosynthesize. Still they split water molecules and release oxygen. And now that oxygen has no choice but to diffuse outward, spreading into the broader ocean, searching for whatever it can oxidize. This moment has been building for perhaps 300 million years. Since the first cyanobacteria evolved oxygenic photosynthesis, the ocean's iron has been rusting out, gradually, relentlessly. The process was never fast enough to notice in a human lifetime, or even in a million human lifetimes, but it was consistent. Every gram of iron removed from solution brought the ocean 1 gram closer to saturation. The buffer was enormous, planetary in scale, but it was finite. And now, in scattered locations around the shallow seas, that buffer is finally exhausted. The iron is gone, the oxygen is free. The transition is not simultaneous across all oceans. It begins in the most productive shallow zones, the places where cyanobacterial activity has been highest and where the local iron supply was smallest. These oxygenated pockets remain isolated initially, surrounded by vast volumes of still anoxic water. Currents mix oxygen-rich water with iron-rich water, and the iron immediately precipitates, creating a boundary layer, a chemical front where the old ocean chemistry meets the new. This front shifts and moves with currents and seasons, advancing and retreating. But the net trend is expansion. Each year, the oxygenated zones grow slightly larger. Each decade, the anoxic zones shrink. The transformation is underway. Only took the better part of 1 billion years to run out of rust, and now there's oxygen with nowhere to go. The cyanobacteria, of course, notice nothing. Their biochemistry is unchanged, their growth rate stable. They have been producing oxygen at roughly the same rate since their evolution, and they will continue to do so regardless of whether that oxygen combines with iron or accumulates in the water. They are not accelerating the process, not responding to the chemical shift happening around them. They are simply continuing to do what they have always done, and the environment is finally beginning to respond. The first organisms to encounter truly oxygenated waters are likely destroyed by it. Anaerobic bacteria that have lived in the shallows, tolerating low oxygen levels but not thriving in them, find themselves in an increasingly hostile environment. The reactive oxygen species, superoxide radicals, hydrogen peroxide, hydroxyl radicals, tear through their cellular machinery. They have no defenses, no enzymes to neutralize these compounds. Populations collapse in the oxygenated zones. Empty ecological niches appear, spaces where anaerobic metabolisms once operated but can no longer survive. For a time, these niches remain empty. The water is too oxygen-rich for anaerobes, but not yet structured in a way that favors aerobic life, which hasn't really evolved yet beyond rudimentary forms. The oxygen begins to diffuse upward toward the ocean surface. In the deepest basins, it is still consumed by reduced chemicals, manganese, sulfur, organic matter, long before it can reach the air. But in shallow seas, particularly those with limited connection to the deep ocean, the oxygen can reach the surface. It sits at the water-air interface, a dissolved gas in equilibrium with the atmosphere above, and now, for the first time, oxygen molecules begin to escape from the ocean into the sky, not in great quantities initially, just a few molecules here and there, wherever the surface water is supersaturated. But it is happening. After 2 billion years of biological activity confined to the water, the waste product of photosynthesis is finally reaching the atmosphere. The scientific uncertainty here involves the spatial pattern of oxygenation. Did the ocean oxygenate from the surface down or from shallow zones outward? Some models suggest that oxygen first accumulated in the upper layers of the open ocean, gradually diffusing downward over millions of years until even the deepest waters became oxygenated. Other models emphasize the role of shallow continental shelves, suggesting that these areas oxygenated first, and that the deep ocean remained anoxic for hundreds of millions of years after the surface became oxygen-rich. The rock record provides evidence for both scenarios in different locations, suggesting that the process was probably not uniform globally. Different ocean basins may have oxygenated at different rates, depending on their connection to the open ocean, their biological productivity, and their supply of reduced chemicals that could consume oxygen. What is clear from multiple lines of evidence is that this is not a smooth, gradual transition. The chemical proxies preserved in rocks from this time period show fluctuations, suggesting that oxygen levels rose and fell repeatedly before stabilizing at higher concentrations. There may have been false starts, periods when oxygen began to accumulate but then crashed back down as new sources of reduced chemicals, perhaps from volcanic activity or tectonic events, consumed the oxygen faster than it could be produced. The Great Oxygenation Event, despite its name, was probably not a single event, but a series of oscillations, a chemical system searching for a new equilibrium over tens of millions of years. The oxygen continues to rise in the shallow zones. Concentrations reach levels that would be considered moderate by modern standards, perhaps a few % of modern atmospheric oxygen, maybe less. It is enough to begin changing the chemistry of the seafloor sediments, enough to oxidize minerals that have remained reduced since Earth's formation. Uranium, for instance, becomes mobile in the presence of oxygen, dissolving from rocks and precipitating in different locations. The isotopic signature of uranium in sediments begins to change around this time, a subtle shift that records the first appearance of oxygen in pore waters between sediment grains. Molybdenum, another element sensitive to oxygen, shows similar shifts. The chemical fingerprints are everywhere once you know how to read them, and still the cyanobacteria photosynthesize. Still they build their stromatolites layer by layer. Still they release oxygen into water that can finally carry it beyond the local environment. The buffer is broken. The iron is depleted. The surface tension, in a chemical sense, has given way. Oxygen is free to spread, to diffuse, to search for whatever it might oxidize. The methane in the atmosphere waits, unaware, as the first oxygen molecules begin their slow journey upward through the water column toward the sky. The first oxygen molecules reach the atmosphere as escapees, not invaders. They bubble out of supersaturated surface waters, rise through the air-sea interface, and enter a sky that has not seen free oxygen in any significant quantity since Earth's formation. The atmospheric residence time for these early oxygen molecules is measured in hours, perhaps days at most. They encounter methane almost immediately. Methane is everywhere. comprising perhaps 0.1% of the atmosphere, 10,000 times more abundant than it will be in the modern world. The two gases are thermodynamic opposites, and in the presence of ultraviolet radiation from the sun, they react. The reaction is not explosive. It proceeds at a rate determined by photochemistry, by the availability of UV light to break chemical bonds and create reactive intermediaries. A methane molecule absorbs a photon and splits, creating a methyl radical. An oxygen molecule absorbs a different photon and splits into two oxygen atoms, each one desperate to combine with something. The radicals find each other in the upper atmosphere and react, forming formaldehyde, then formic acid, then carbon dioxide and water. The products are stable, unreactive in comparison to the starting materials. The methane is destroyed, the oxygen is consumed, and the greenhouse effect weakens by an imperceptible fraction. This process has been happening in trace amounts since cyanobacteria first evolved, but always at a rate so slow that it couldn't overcome the continuous production of methane by methanogenic bacteria. The methane was being replenished faster than it could be destroyed, maintaining atmospheric concentrations in equilibrium, but now the balance is shifting. More oxygen is escaping from the ocean as the ion buffer depletes. More methane is being destroyed in the upper atmosphere, and the methanogens, living in deep ocean sediments far from the oxygenated surface, cannot increase their production fast enough to compensate. The equilibrium is breaking. Only took 2 billion years to build an atmosphere, and a few million to dismantle it, molecule by molecule. The methane concentration begins to decline. Not quickly. This is still a process that operates on geological timescales, but measurably. Proxies preserved in ancient soils, in the carbon isotope ratios of organic matter, in the types of minerals that form under different atmospheric conditions, all suggest that methane levels begin dropping around 2.4 billion years ago. The drop is not steady. There are periods when methane concentrations rebound, perhaps due to increased volcanic activity or changes in ocean circulation that affect oxygen escape rates. But the overall trend is downward. The greenhouse is weakening. The sky begins to change color. The orange methane haze that has characterized Earth's atmosphere for over 1 billion years starts to thin. The organic molecules that scatter light and create that distinctive tint are produced by methane photolysis. And as methane concentrations decline, so does the haze. The atmosphere becomes clearer, more transparent. The blue of Rayleigh scattering, light scattered by nitrogen molecules, begins to assert itself. Though the atmosphere is still far from the deep blue of modern times, the sun, shining through less haze, appears slightly brighter, slightly whiter. The changes are subtle, taking place over millions of years, far too slow to be perceived except by the patient eye of geological analysis. The temperature begins to drop. Methane is roughly 30 times more effective as a greenhouse gas than carbon dioxide over a century-long time scale, and its removal from the atmosphere has immediate climate consequences. The faint young sun, already providing less energy than it will in later epochs, becomes insufficient to maintain Earth's warmth without the methane blanket. Heat begins radiating into space more efficiently. The equatorial oceans, which have remained warm enough to support robust cyanobacterial communities, begin to cool. The cooling is not catastrophic initially, perhaps a degree or two per million years, but it is relentless. And there is no mechanism to stop it. The oxygen keeps rising, the methane keeps declining, and the planet keeps cooling. The scientific debate here centers on whether this cooling was gradual or abrupt. Some models suggest a relatively smooth transition, with temperatures declining steadily over tens of millions of years as methane was gradually destroyed. Other models propose the possibility of a runaway cooling event, a point at which declining temperatures reduced biological productivity, which reduced oxygen production, which should have slowed methane destruction, but instead allowed ice to form, which increased Earth's reflectivity, which accelerated cooling regardless of atmospheric chemistry. The rock record from this time period is sparse and ambiguous, and different research groups interpret the same data in different ways. What is preserved, however, are the earliest glacial deposits from this era. Tillites, rocks formed from glacial debris, appear in the geological record around 2.4 to 2.3 billion years ago, in locations that were likely at low latitudes based on paleomagnetic data. This suggests glaciation extending toward or even across the equator, an ice age of extraordinary severity. These deposits are the first evidence of what researchers call the Huronian glaciation, named after rock formations in Canada where the glacial deposits are particularly well preserved. The glaciation will last, on and off, for perhaps 300 million years, making it one of the longest cold periods in Earth's history. And it begins here, with the destruction of methane by oxygen, with the dismantling of the greenhouse that kept the Archean world warm. The cyanobacteria, architects of this transformation, continue their work even as the climate deteriorates. They are adapted to warm conditions, and as temperatures decline, their productivity drops in many regions. But they persist, particularly in the remaining warm refugia near the equator or in geothermally heated coastal zones. They continue to photosynthesize, continue to produce oxygen, continue to drive the very process that is cooling the planet and making life more difficult for themselves. There is no feedback mechanism that would allow them to slow down, no way for the biological system to sense the climate consequences of its own chemistry. Evolution operates on individual fitness, not planetary well-being, and any cyanobacterium that stopped producing oxygen would simply be outcompeted by its neighbors that continued. The sky learns to burn. Not literally, there are no flames, no visible combustion, but chemically. The upper atmosphere becomes an oxidizing zone, a place where methane is broken down and converted to carbon dioxide and water. The process is silent, invisible, and ultimately transformative. The orange fades, the warmth dissipates, and somewhere in the high atmosphere, the first ozone molecules begin to form as oxygen splits and recombines, creating a shield that will eventually protect the surface from ultraviolet radiation. But that is still far ahead. For now, there is only the burning, the quiet, molecular destruction of the greenhouse, one methane molecule at a time. The ice begins at the poles, as ice does, but these are not the familiar ice caps of recent Earth history. The poles in the Paleoproterozoic are positioned differently. The continents are arranged in configurations that no longer exist, and the ice that forms there finds itself in shallow seas and along low-lying coastlines. The water freezes first in winter, creating sea ice that extends outward from the land. In spring, some of this ice melts, but not all of it. The summer sun, weakened by the thinning methane greenhouse and already faint compared to the modern star, cannot fully reverse the winter's work. A portion of the ice persists. The following winter adds more. The ice shelf grows. The expansion is self-reinforcing. Ice reflects sunlight far more efficiently than liquid water or dark rock, where the ocean absorbs perhaps 90% of incoming solar radiation. Warming itself in the process, ice reflects 70% or more, bouncing that energy back into space before it can heat anything. This is the ice albedo feedback, and it is among the most powerful climate amplifiers in Earth's system. As ice cover increases, the planet's reflectivity increases, which reduces the amount of absorbed sunlight, which cools the planet further, which allows more ice to form. The process feeds on itself, and once it begins in earnest, it becomes difficult to stop. The glaciers start moving. Ice accumulates on land and begins to flow under its own weight. carving valleys, scouring bedrock, carrying debris embedded in its base like geological sandpaper. The flow rates are slow by human standards, meters per year. Perhaps, but they are inexorable. Rock flour, the fine powder created by glacial grinding, washes out from beneath the ice in summer meltwater streams, turning coastal waters milky gray. This sediment will eventually become tillite, the diagnostic rock of ancient glaciation, a chaotic mixture of angular boulders and fine clay cemented together and compressed over geological time. The tillites forming now will persist for billions of years, evidence of ice in an era when Earth should have been warmer, protected by a methane greenhouse that has now failed. The ice reaches toward the equator. Paleomagnetic data from glacial deposits of this age suggest that some of these formations originated at latitudes of 30 degrees or less, well within what would normally be tropical zones. This is extraordinary. Modern glaciation barely extends past 60 degrees latitude even during ice ages. But the Huronian glaciation is operating under different rules. The sun is fainter. The greenhouse gases are depleted, and there is no vegetation on land to alter surface albedo or modify water cycling. The continents are bare rock and sand, offering no resistance to the advance of ice. The glaciers crawl toward the tropics, following coastlines, filling valleys, building ice sheets that in some regions may have been kilometers thick, only took a few million years to freeze a planet that had been warm for 2 billion. The speed is remarkable in geological terms, though it would still be imperceptible to any observer living through it. Temperatures don't crash overnight. The ice doesn't appear suddenly. Instead, each winter is slightly colder than the last, each summer slightly less effective at melting the previous winter's accumulation. Coastal communities of stromatolites, those bacterial cities that have persisted for over 1 billion years, find themselves in increasingly hostile conditions. The water grows colder. Sea ice forms in shallows where it never formed before. Some communities die out. Others retreat to warmer refugia, following the narrowing band of habitable climate toward the equator. The ocean's circulation changes in response to the cooling. Cold water, being denser than warm water, sinks in the polar regions and flows along the seafloor toward the equator, displacing warmer water upward and poleward in a global conveyor belt. This thermohaline circulation intensifies as the temperature gradient between poles and equator increases. The deep ocean becomes cold, very cold, approaching the freezing point in some basins. The cold water is also oxygen poor. Oxygen is more soluble in cold water, but the water sinking from the surface is coming from regions where ice cover prevents gas exchange with the atmosphere. The deep ocean begins to stratify with cold, anoxic bottom waters overlain by warmer, occasionally oxygenated surface layers. This stratification will persist throughout much of the glaciation. The cyanobacteria adapt or die. Those populations living in the cooling tropics face a productivity crisis. Photosynthesis is temperature dependent, and as water temperatures drop from perhaps 30 degrees Celsius to 20 or 15, metabolic rates slow. Less photosynthesis means less oxygen production, which might seem like it would slow the methane destruction and allow the greenhouse to recover. But the feedback is not fast enough. The ice is already established, the albedo effect already operating, and the climate system has momentum in the direction of cooling. The cyanobacteria can no longer produce enough greenhouse destruction to significantly impact the trajectory. The planet is entering a new climate state, and biology must now adapt to changes it inadvertently triggered. The mystery, preserved in the Huronian glacial record, is its episodic nature. The rock formations show multiple glacial periods separated by warmer intervals. There are at least 3, possibly 4 distinct glacial advances recorded in the tillites and associated sediments, each separated by non-glacial deposits indicating periods of ice retreat. This suggests that the Huronian glaciation was not a single prolonged freeze, but a series of ice ages punctuated by warmer interludes. What caused these fluctuations? Orbital variations, perhaps. Similar to those that drove Pleistocene ice ages millions of years later, volcanic activity possibly, releasing carbon dioxide that temporarily rewarmed the planet before the oxygen-methane reaction reasserted control. Or variations in ocean circulation that periodically delivered warmer water to the poles and melted the ice sheets. The evidence is insufficient to choose between these hypotheses. What is certain is that the ice persists for an extraordinary length of time. Conservative estimates place the Huronian glaciation at lasting from about 2.4 to 2.1 billion years ago, 300 million years of intermittent glaciation. That is longer than the entire Phanerozoic eon, longer than the span from the Cambrian explosion to the present day. It is difficult to comprehend climate persistence on this time scale. The ice accumulates, melts, accumulates again, always returning, always reasserting itself whenever conditions permit. The planet has found a new equilibrium, colder than before, and it will remain there until something fundamental changes in Earth's atmosphere or orbit or internal heat production. The glaciers carry boulders hundreds of kilometers from their source. These erratics, dropped when the ice finally melts, will lie on the landscape like geological puzzles, rocks of one type sitting on terrain of a completely different composition. Later researchers will use these erratics to reconstruct ice flow patterns, to map the extent of ancient glaciers, to understand the geometry of ice sheets that existed 2 billion years before humans evolved to study them. The glaciers also carve striations into bedrock, parallel grooves that record the direction of ice movement. These striations are preserved in rocks now exposed at Earth's surface, their orientations still readable, pointing in directions that reveal the centers of ancient ice accumulation. The equator remains unfrozen. Probably. The evidence suggests that even at the coldest points of the Huronian glaciation, there were ice-free regions in the tropics where liquid water persisted. This prevents a complete snowball Earth scenario. At least during this particular event, open water allows for continued photosynthesis, continued oxygen production, and, crucially, continued weathering of silicate rocks, which consumes carbon dioxide and maintains the planet's long-term carbon cycle. If the entire planet had frozen solid, these processes would have stopped, potentially locking Earth into a permanent ice house from which escape would require extraordinary volcanic CO2 emissions. That fate is avoided, barely. The ice finds the equator, reaches toward it, perhaps even touches it in the coldest intervals, but does not completely close the circle. The stromatolites persist in the remaining warm zones, reduced in extent but not eliminated. They continue building their limestone structures, continue producing oxygen, though at rates far below those of the warm Archean. The oxygen they produce still escapes to the atmosphere, still destroys the remaining methane, but with the greenhouse already collapsed and temperatures already low, the additional cooling effect is minimal. The system has reached a new state, a cold equilibrium, and will remain there for hundreds of millions of years. The ice age has begun. The sky is no longer orange. The seas are cold, and somewhere beneath the glaciers, beneath the ice sheets grinding slowly equatorward, the stromatolites wait in darkness. The light that penetrates ice is blue and weak, where seawater might allow photosynthesis down to depths of 100 meters in clear conditions. Ice reduces that photic zone to a fraction of its former extent. The ice itself, even relatively clear glacial ice, absorbs and scatters light, particularly the red wavelengths that many photosynthetic organisms prefer. What filters through to the water beneath is dim, blue-shifted, barely sufficient to sustain life. And yet, life persists. In the channels between ice and bedrock, in the pockets of liquid water maintained by geothermal heat or tidal pumping, in the thin film of unfrozen water that exists at the ice-ocean interface even at temperatures below zero. The cyanobacteria continue their patient work. These refugial populations are living at the edge of metabolic viability. Photosynthesis at low light levels is inefficient, barely yielding enough energy to offset the costs of cellular maintenance and reproduction. Growth rates slow to near zero. Cell division happens perhaps once per month, where it might have occurred daily in the warm Archean seas. The stromatolites these bacteria build grow so slowly that their laminae are barely distinguishable, requiring microscopic analysis to detect the annual or decadal layering. But they grow. The structures persist. The oxygen production continues, albeit at a fraction of pre-glacial rates. The darkness is not absolute during summer months, when the sun rises higher in the sky and the days lengthen. Enough light penetrates the ice to drive photosynthesis at rates approaching those of deeper ocean environments. The bacteria respond with a surge of activity, producing oxygen, reproducing, storing energy for the long winter to come. The oxygen they produce has nowhere to escape. The ice forms a physical barrier between the water and the atmosphere, so it accumulates beneath the ice, creating oxygen-rich pockets that exist in isolation from the broader ocean. These pockets become oases, zones where oxygen concentrations reach levels far higher than the average ocean, even higher perhaps than in the pre-glacial shallow seas. Only took a global glaciation to create the first truly oxygen-rich marine environments, locked under ice where nothing can use them. The irony is exquisite. The cyanobacteria, having inadvertently triggered the cooling that led to glaciation, now find themselves in the best possible conditions for oxygen accumulation. Isolated pools where their waste product cannot escape and cannot be consumed by reaction with reduced minerals, because the ice prevents mixing with the broader ocean. These sub-ice environments are evolutionary laboratories, places where high oxygen concentrations persist for the first time in Earth's history. Any organism that evolves oxygen tolerance or oxygen utilization will find extraordinary advantages here. The ice above is in constant motion, even though it appears static. The glaciers flow, carving and recarving the landscape, grinding bedrock into flour, occasionally carving icebergs into the frigid seas. The ice sheets thicken in their centers and spread outward, driven by their own weight, creating radial flow patterns that transport ice from accumulation zones to ablation zones where it melts or sublimates. The movement is slow enough that the ice appears solid, frozen in place. But given enough time, decades, centuries, the displacement is significant. Boulders embedded in the ice travel hundreds of kilometers from their origin. Striations carved into bedrock record the passage of countless tons of ice sliding overhead. Beneath the ice sheets on land, subglacial lakes form in topographic depressions. These lakes are isolated from the atmosphere, trapped between bedrock and ice perhaps kilometers thick, sustained by geothermal heat or the pressure melting of ice at depth. The water in these lakes is cold, near freezing, but it is liquid. And where there is liquid water, there is the potential for life. Some of these lakes may harbor cyanobacterial communities, dark-adapted strains living off the dim light that filters through the ice, or perhaps switching to alternative metabolisms that don't require photosynthesis. Others may be too dark, too isolated, supporting only chemosynthetic bacteria that extract energy from minerals and gases dissolved in the water. The lakes are ecosystems unto themselves, cut off from the rest of the planet's biosphere. The scientific challenge in understanding this period is the scarcity of well-preserved biological indicators. Glaciation tends to erase evidence. The ice sheets scour away sediments, grind up fossils, remove the very rocks that would tell us what life was doing during these frozen intervals. What remains are a few scattered deposits in regions that escaped glaciation, thin layers of sediment from tropical seas. occasional stromatolites from ice-free zones, chemical signatures in minerals that hint at biological activity. We infer that life persisted, that the cyanobacteria survived the cold, because we see them reappear in the rock record after the glaciation ends. But the details of their survival, how widespread they were, how their populations fluctuated, what adaptations they evolved, these remain largely mysterious. What we can say with confidence is that photosynthesis did not stop. The carbon isotope record shows continued fractionation consistent with biological activity throughout the Huronian glaciation. The oxygen production may have slowed, but it didn't cease. The cyanobacteria found a way, as life so often does, to persist through unfavorable conditions. They retreated to refugia. They adapted to low light. They survived beneath the ice, in the darkness, producing oxygen that would eventually contribute to the transformation of Earth's atmosphere once the glaciers retreated and the oceans could once again exchange gases freely with the air. The ice above them grows thicker in some regions, thinner in others, responding to the balance between snowfall and melting, between accumulation and ablation. The glaciers advance during the coldest periods, retreat during the warmest intervals within the glaciation. The sub-ice ecosystems expand and contract accordingly, their populations waxing and waning with the availability of light and liquid water. The system is dynamic, even in the depths of an ice age. Nothing is truly static on a planet with active tectonics, orbital variations, and living organisms adapting to changing conditions. The stromatolites beneath the ice record this variability in their structure. During times of better light penetration, the growth layers are more pronounced, reflecting higher productivity. During the darkest periods, growth nearly stops, creating gaps in the stromatolitic record, hiatuses that represent years or decades when conditions were too unfavorable for significant mineral precipitation. Reading these structures is like reading an ice core in reverse. Instead of analyzing layers of ice to reconstruct ancient climate, we analyze layers of limestone to reconstruct ancient light levels, productivity, and ocean chemistry beneath long-vanished glaciers. The information is fragmentary, difficult to extract, but it is there, preserved in stone, waiting for patient analysis. The darkness persists. The ice thickens. And beneath it all, in the cold and the dim, the cyanobacteria wait. They photosynthesize when they can. They respire when they cannot. They endure, as they have endured for over 1 billion years, as they will endure for billions more. The great oxygenation event continues, even in the ice age, even in conditions that seem utterly hostile to life. The oxygen accumulates in isolated pockets beneath the glaciers. The transformation proceeds. And somewhere in this frozen world, in some sub-ice pool rich with oxygen and devoid of predators, evolution is working on something new. The uranium begins to move. This is not a dramatic statement. Uranium is not given to drama, but it represents a profound change in Earth's surface chemistry. Uranium in its reduced state. Uranium IV is essentially insoluble in water. It sits in minerals, locked in place, immobile for billions of years. But uranium in its oxidized state, uranium-6, dissolves readily, forming soluble complexes that can be transported by groundwater and rivers, precipitated in different environments, concentrated in ways that the reduced form never could be. And uranium-6 requires oxygen to form. The appearance of mobile uranium in the rock record is a chemical marker, a signature that tells us when oxygen finally penetrated into soils and sediments in concentrations sufficient to oxidize even the most resistant minerals. That signature appears in the geological record around 2.4 to 2.3 billion years ago. Coincident with the beginning of the Huronian glaciation and the collapse of the methane greenhouse. The timing is not coincidental. As oxygen escapes from the ocean and begins accumulating in the atmosphere, even in small concentrations, it starts to alter the chemistry of Earth's surface. Rain falling through an oxygen-bearing atmosphere carries dissolved oxygen into soils. Groundwater percolating through rock encounters oxygen and becomes oxidizing. The transformation is subtle. Atmospheric oxygen concentrations during this early phase are probably less than 1% of modern levels. Perhaps much less, but it is sufficient to mobilize uranium. The isotopic ratios of uranium preserved in ancient river deposits show this mobilization clearly. Before the Great Oxygenation Event, uranium isotopes in sediments reflect the composition of their source rocks. With minimal fractionation, evidence that uranium was transported mechanically as solid particles, not dissolved in water after the oxygenation begins. The isotope ratios change. Different isotopes of uranium behave slightly differently when dissolved and reprecipitated, creating a fractionation pattern that is diagnostic of transport in solution. The change is recorded in rocks from multiple continents, suggesting a global transformation of surface chemistry. The uranium clock starts ticking, and it records the moment when Earth's surface began to rust. Only took 2 billion years to create conditions where rocks could dissolve. And now the continents are learning to weather in new ways. Weathering, the breakdown of rock by chemical and physical processes, has been operating since Earth formed, but it has been dominated by reactions that don't require oxygen. Water plus carbon dioxide creates carbonic acid, which dissolves minerals. Temperature changes crack rocks. Mechanical erosion grinds stone to sand. These processes continue in the oxygenated world, but they are joined by oxidative weathering, a fundamentally more aggressive form of chemical attack. Iron-bearing minerals rust. Sulfide minerals convert to sulfates. Reduced carbon in rocks combines with oxygen, releasing carbon dioxide. The continents begin to corrode in ways they never have before. The rivers carry the products of this weathering to the oceans. Dissolved sulfate increases in concentration, a shift visible in the sulfur isotope composition of marine minerals. Molybdenum, another element that becomes mobile in the presence of oxygen, begins to accumulate in ocean sediments at higher concentrations. These trace element enrichments are subtle. We're talking about parts per million or parts per billion, but they are measurable and consistent across multiple geological sections. They tell a story of continental weathering accelerating, of oxidizing conditions spreading from the atmosphere into soils and groundwater, of the surface environment transforming from reduced to oxidized over a span of perhaps 10 to 20 million years. The soils themselves begin to change in character. Prior to oxygenation, soils were dominated by reduced iron minerals, green and gray in color, rich in ferrous iron. After oxygenation, red soils appear for the first time, red beds, as geologists call them, composed of iron oxides and hydroxides, the rust products of weathering in an oxygen-rich environment. These red beds are not universally present immediately after the Great Oxygenation Event. The oxygen concentrations are still low, and many environments remain reducing, but they begin to appear in the rock record, first sporadically, then more commonly. They are a visible signature of the new atmospheric chemistry, written in the color of the land itself. The mystery that remains partially unresolved is how quickly atmospheric oxygen rose during this transition. Did it increase gradually over tens of millions of years, asymptotically approaching some equilibrium value? Or were there rapid pulses, periods when oxygen spiked to relatively high levels before crashing back down? The uranium isotope record, the sulfur isotope record, and various other proxies give somewhat conflicting signals. Some data suggest a relatively rapid rise, a few million years from anoxic to oxygenated conditions. Other data suggest a more protracted transition with multiple reversals. Part of the difficulty is that these proxies respond to different aspects of the oxygen cycle, atmospheric concentration versus ocean chemistry versus redox state of soils, and these can be decoupled from each other under certain conditions. What seems clear is that the transition was not smooth. There are intervals during the Paleoproterozoic when the chemical signatures suggest a return to more reducing conditions, episodes when oxygen concentrations dropped, or when anoxic conditions briefly returned. These may reflect periods of intense volcanic activity, which releases reduced gases that consume oxygen, or they may reflect changes in biological productivity, fluctuations in the rate at which cyanobacteria produce oxygen, or perhaps they are artifacts of local environmental conditions, chemical changes in specific ocean basins or continental regions that don't reflect global atmospheric chemistry. Disentangling global signals from local noise is one of the great challenges in studying Earth's early atmosphere. The uranium continues its migration, dissolving from source rocks, traveling in groundwater, precipitating in oxygen-poor environments like organic-rich sediments, where bacteria reduce the uranium back to its insoluble form. This process creates uranium deposits, concentrations of the element far above normal crustal abundances. Some of these deposits will eventually become economically important, sources of uranium for nuclear reactors and other applications. But that is billions of years in the future. For now, they are simply chemical anomalies, places where oxidative weathering and microbial reduction conspire to concentrate an element that was previously diffuse and immobile. The continental crust is being remade, slowly and chemically. The surface layers, the top meters to tens of meters, are no longer in equilibrium with the atmosphere. They were formed under reducing conditions, and now they are exposed to oxygen. The minerals react, transforming from their reduced forms to oxidized equivalents. The rock doesn't change shape or structure, but its chemistry and color shift. Gray becomes red, green becomes brown. Shiny sulfide minerals tarnish and crumble to sulfate. The transformation is superficial in a geological sense. It affects only the surface, while the deep crust remains unchanged, but it is permanent. Once oxidized, these rocks will remain oxidized unless buried and reduced by later geological processes. The uranium clock continues ticking, recording in its isotopes the presence of oxygen, the intensity of weathering, the chemical state of Earth's surface. It is a clock that will run for billions of years, through ice ages and warm periods, through supercontinent cycles and mass extinctions, always recording, always fractionating, always providing a chemical memory of the conditions under which it was transported and deposited. And it all begins here, in the Paleoproterozoic. When oxygen first rises and the uranium first learns to move, the stromatolites continue their patient construction. In the ice-free tropics, in shallow embayments where the water remains liquid year-round, the cyanobacterial mats persist in building their limestone domes. The structures grow more slowly now than they did in the warm Archean. The cooler water temperatures reduce metabolic rates, and the lower light levels that penetrate through a clearer but colder atmosphere provide less energy for photosynthesis. But the growth continues, layer upon layer, millimeter by millimeter. The stromatolites rise from the seafloor, recording in their architecture the passage of time and the state of the ocean chemistry. The laminae within these structures are remarkably regular in some specimens, suggesting an annual or seasonal rhythm to their formation. During periods of high productivity, likely the summer months when light is strongest and water warmest, the cyanobacteria grow rapidly and precipitate calcium carbonate at higher rates. The resulting layers are thicker, richer in organic matter, darker in color when viewed in cross-section. During winter or during periods of low productivity, growth slows. The layers become thinner, lighter in color, dominated by fine-grained carbonate precipitated more slowly or by sediment that drifted in from elsewhere. The alternation creates visible banding, a barcode of ancient seasons preserved in stone. These structures are among the oldest continuously forming biological constructions on Earth. Stromatolites have been building themselves since at least 3.5 billion years ago, possibly earlier, and they will continue in various forms until the present day. The same basic architecture, microbial mats trapping sediment and precipitating minerals, has persisted through almost the entire history of life on Earth. It is a testament to the effectiveness of a simple strategy: grow in shallow water, capture sunlight, produce organic matter, and inadvertently create stone. The stromatolites are not trying to build anything. They have no goal, no purpose beyond the metabolic imperatives of the bacteria that compose them. The limestone domes are byproducts, accidents of chemistry occurring at the interface between life and geology. Only took 3 billion years to perfect a design, and then evolution stuck with it. The conservatism is remarkable. Stromatolites from the Archean look fundamentally similar to stromatolites from the Paleoproterozoic, which look similar to stromatolites from the modern world. The details change, the species of bacteria involved, the exact chemistry of the carbonate, the association with other organisms, but the basic form persists. This is not because stromatolites are optimal in some engineering sense, it is because they work well enough. And in the absence of intense biological competition or predation, there is no pressure to evolve different forms. The strategy succeeds by being simple and robust. The oxygen these stromatolites produce during daylight hours escapes into the water column, where it encounters an ocean that is still largely anoxic below the surface layers. The oxygen diffuses downward, reacting with reduced iron and sulfur in the water, being consumed before it can reach significant depths. In the modern ocean, oxygen penetrates to great depths because wind-driven mixing and thermohaline circulation bring surface water down into the abyss. But in the Paleoproterozoic, with ice covering much of the polar regions and limiting gas exchange, the deep ocean remains isolated from the atmosphere. It is a two-layer system, an oxygenated surface extending down perhaps a few tens of meters, and anoxic depths extending to the sea floor. The stromatolites live in the oxygenated layer, producing the very oxygen that maintains it. The carbonate they precipitate contains chemical information about the water in which it formed. Oxygen isotopes in the carbonate reflect temperature. Colder water produces carbonate enriched in the heavy isotope. Warmer water produces carbonate enriched in the light isotope. Carbon isotopes reflect the source of the carbon. Carbonate derived from organic matter has a different isotopic signature than carbonate precipitated directly from dissolved carbon dioxide. Trace elements incorporated into the carbonate lattice, magnesium, strontium, barium, vary with ocean chemistry and can be used to infer seawater composition. Each stromatolite is a recording device, a chemical archive of the conditions under which it grew. The mystery preserved in these structures is the question of biological specificity. Are all stromatolites created by cyanobacteria? Or can other types of bacteria create similar structures? Modern stromatolites are dominated by cyanobacteria, but they also contain diverse communities of other bacteria, sulfur oxidizers, methanogens, heterotrophs that consume organic matter. In ancient stromatolites, we cannot always identify the specific organisms involved. We see the structures, the laminae, the chemical signatures of biological activity, but the bacteria themselves are rarely preserved as fossils. We infer cyanobacterial involvement from the presence of oxygen-requiring minerals, from the carbon isotope signatures consistent with photosynthesis. But the inference is indirect. Other types of bacteria might create similar structures under different conditions. What is certain is that these stromatolites are recording the great oxygenation event in real time. The stromatolites that grow before the oxygenation are surrounded by water rich in dissolved iron. They precipitate iron-bearing carbonates, minerals with a distinctive greenish color. The stromatolites that grow during and after the oxygenation are surrounded by water where the iron has been precipitated out. They form iron-poor carbonates, whiter and more similar to modern limestone. The transition is visible in cross-section. Older layers green, younger layers white, a chemical record of the ocean's iron being stripped away by reaction with oxygen. The architecture of the stromatolites also varies with environment. In high-energy settings, shallow zones with strong currents or wave action, the structures are low and broad, resistant to physical disruption. In quiet water, they grow taller, forming columns or even branching structures that reach upward toward the light. The morphology is not genetically determined. The same bacterial strains can produce differently shaped stromatolites depending on environmental conditions. This makes stromatolites useful as paleoenvironmental indicators. By examining their shape and internal structure, we can infer the water depth, energy level, and light availability of the environment in which they formed. Some stromatolites from this period show evidence of disturbance, layers that are tilted, truncated, or eroded before subsequent growth resumes. These features suggest storm events, periods when unusually strong currents or waves disrupted the mats before they could fully lithify. The disturbances are then healed by new bacterial growth, creating an unconformity within the structure, a time gap recorded in stone. These internal unconformities are common in stromatolites, evidence that even in the relatively quiet environments where they thrive, occasional high-energy events reshape the seafloor. The stromatolites persist. They continue building, continue photosynthesizing, continue producing oxygen and carbonate in the shallow tropical seas that remain ice-free throughout the Huronian glaciation. They are living fossils in the most literal sense, ancient organisms still performing ancient processes, largely unchanged by the billions of years that have passed since their first appearance. They are monuments to biological conservatism, to the power of a successful strategy repeated across deep time. And they are witnesses to the transformation happening around them, recording in their limestone layers the slow oxygenation of Earth's ocean and atmosphere, the greening of ancient seas, the rust and the cold and the oxygen that will eventually enable complexity they cannot imagine. Somewhere in the oxygen-rich pockets beneath the ice, or in the shallow tropical waters where stromatolites still thrive, or perhaps in multiple locations independently. A cell evolves the machinery to breathe poison. This is aerobic respiration, the process of using oxygen to extract energy from organic molecules, and it represents one of the most significant metabolic innovations in the history of life. The chemistry is elegant. Glucose plus oxygen yields carbon dioxide, water, and approximately 38 molecules of ATP, the energy currency of cells. Compare this to fermentation, which yields only 2 ATP molecules from the same glucose, and the advantage becomes obvious. Aerobic respiration is roughly 19 times more efficient at extracting energy from food, but efficiency comes at a cost. Oxygen is still toxic. Using it as part of metabolism means bringing it into close contact with cellular machinery, creating opportunities for it to damage proteins, lipids, and DNA. The first aerobic organisms must evolve extensive antioxidant systems, enzymes like catalase and superoxide dismutase that neutralize reactive oxygen species before they can cause harm. These enzymes are complex, requiring metals like iron or manganese as cofactors, and their evolution probably proceeds gradually through intermediate forms that offer partial protection. The earliest aerobic organisms likely operate at much lower oxygen concentrations than modern aerobic life, living in environments where oxygen is present but not abundant, where the benefits of aerobic respiration outweigh the damage from oxidative stress. The threshold concentration, the oxygen level above which aerobic respiration becomes advantageous over anaerobic metabolism, is estimated at around 1% of present atmospheric levels, perhaps less. This is called the Pasteur point, and it represents a fundamental transition in the metabolic economics of life. Below this concentration, the energy gained from using oxygen doesn't offset the costs of maintaining antioxidant defenses and repairing oxidative damage. Above it, aerobic organisms can outcompete anaerobes in any environment where organic matter is available. The Great Oxygenation Event brings atmospheric oxygen to levels near or above this threshold, creating for the first time in Earth's history widespread environments where aerobic respiration is viable. Only took half the age of the universe to invent breathing, and the invention happens quietly. Without fanfare or fossil record, we cannot identify the first aerobic organism. We have no fossils of the moment when oxygen shifted from poison to resource. What we have is biochemistry. The molecular machinery of aerobic respiration is so complex and so similar across all modern aerobic organisms that it must have evolved once, or at most, a few times. Early in Earth's history, all aerobic life, bacteria, archaea, fungi, plants, animals, uses variations of the same basic pathway, the same electron transport chains, the same coupling of oxidation to ATP synthesis. This biochemical unity points to a common origin, to a moment in the Paleoproterozoic when one lineage figured out how to breathe and all its descendants inherited the trick. The earliest aerobic organisms are probably bacteria. They are small, adaptable, capable of rapid evolution under selective pressure. They live in environments where oxygen concentrations fluctuate, shallow waters where cyanobacterial activity produces oxygen during the day but where concentrations drop at night, or interface zones between oxygenated surface waters and anoxic depths where mixing creates gradients. These environments favor metabolic flexibility, organisms that can switch between aerobic and anaerobic pathways depending on oxygen availability. Such facultative aerobes may be the intermediate forms, the stepping stones between purely anaerobic life and obligate aerobes that cannot survive without oxygen. The competitive advantage of aerobic respiration is enormous once oxygen becomes reliably available. An aerobic bacterium can grow faster, reproduce more quickly, outcompete anaerobes for the same resources. The effect cascades through ecosystems. In oxygen-rich environments, aerobic organisms come to dominate. Anaerobes retreat to oxygen-poor niches, deep sediments, anoxic basins, the intestines of animals that won't evolve for another 1.5 billion years. The metabolic map of the biosphere reorganizes, with aerobic metabolism claiming the productive, oxygen-rich zones and anaerobic metabolism persisting in refugia. The scientific uncertainty here involves the timing and the phylogeny. When exactly does aerobic respiration evolve? Molecular clock estimates, which use mutation rates to infer the timing of evolutionary divergences, give dates ranging from about 3 billion to 2 billion years ago, a spread that encompasses much of the Archean and early Proterozoic. The uncertainty reflects the difficulty of calibrating molecular clocks for events so far in the past, where the fossil record provides few constraints, different assumptions about mutation rates, generation times, and the tempo of evolution yield different dates. The rock record provides only indirect evidence, chemical signatures suggesting oxygen presence, but not direct proof of aerobic organisms. What we can say with confidence is that aerobic respiration is established by the mid-Proterozoic, and, probably much earlier, by 8 billion years ago. We see fossils of organisms that almost certainly were aerobic, large, complex cells that would require the energy density of aerobic metabolism to maintain themselves. Working backward from that point, and considering the time required for aerobic respiration to evolve and spread, most researchers place the origin somewhere in the Paleoproterozoic, coincident with or shortly after the Great Oxygenation Event. The oxygen creates the opportunity, evolution seizes it, and the biosphere fundamentally changes. The energetic revolution enables other innovations. With more ATP available, cells can afford to be larger, more complex, more active. They can support internal structures, maintain concentration gradients across membranes, power molecular machines that would be uneconomical in an anaerobic cell. Size increases are visible in the fossil record. Cells from after the Great Oxygenation Event are on average larger than cells from before, though the difference is subtle and the trend is not universal. Complexity increases, though slowly. The full elaboration of eukaryotic cell structure, nucleus, mitochondria, complex organelles, will take hundreds of millions of years more. But the foundation is laid here, in the moment when oxygen shifts from waste to resource. The aerobic organisms spread. They colonize the oxygen-rich surface waters, the oxidized sediments, the shallow seas where cyanobacteria produce oxygen faster than it can be consumed. They begin to contribute to the oxygen cycle themselves. Aerobic respiration consumes oxygen, providing a biological sink that partly offsets the production by photosynthesis. The balance between production and consumption will determine the long-term trajectory of atmospheric oxygen. If production exceeds consumption, oxygen continues to rise. If consumption matches production, oxygen stabilizes. The system is searching for equilibrium, and it will take tens of millions of years to find it. The cell that learned to breathe, whatever it was, wherever it lived, left no fossil that we can recognize. But its descendants are everywhere. Every aerobic organism alive today, from soil bacteria to blue whales, from yeasts to giant sequoias, carries in its biochemistry the legacy of that first innovation. The electron transport chains, the cytochromes, the coupling of oxidation to phosphorylation, all of it traces back to that moment in the Paleoproterozoic when oxygen stopped being only a poison and became, for at least some organisms, the key to abundance. The threshold has been crossed. The aerobic world begins. The continents begin to blush. This is not metaphor but chemistry. Iron in exposed rocks reacting with atmospheric oxygen, forming iron oxides that stain the land surface red. These are the red beds, and their appearance in the geological record marks a fundamental shift in continental weathering. Before the Great Oxygenation Event, soils and sediments are dominated by reduced iron minerals, gray-green siltstones, olive-colored shales, rocks that formed under anoxic conditions and retained their reduced chemistry. After oxygenation begins, red beds appear sporadically at first, then with increasing frequency, spreading across the continents wherever surface conditions allow oxidative weathering to proceed. The process begins with rainwater. Rain falling through an oxygen-bearing atmosphere dissolves small amounts of oxygen, becoming weakly oxidizing. This oxygenated water percolates into soils, seeps through fractured rock, flows along groundwater pathways. Everywhere it travels, it oxidizes. Iron-bearing minerals, magnetite, pyrite, iron silicates react with the dissolved oxygen, converting ferrous iron, Fe2+, to ferric iron, Fe3+. Ferric iron is insoluble and precipitates as iron oxides and hydroxides, hematite, goethite, limonite, minerals that range in color from brick red to rust brown to ochre yellow. The rocks don't change structure, but they change color, and that color change is permanent, locked in place as the minerals crystallize. The red beds accumulate in river systems first, floodplains and alluvial fans, places where rivers deposit sediment eroded from the continents, become the canvas on which oxidative weathering paints its signature. The sediments are laid down as usual, sand and silt carried by flowing water, deposited when the current slows, but they are exposed to atmospheric oxygen during and after deposition. The iron oxidizes in place, cementing the grains together with red iron oxide, creating sandstones and siltstones that are distinctively colored. These red bed sequences can be hundreds of meters thick, representing millions of years of deposition under oxidizing conditions. Only took 2 billion years to invent rust, and now the continents are covered in it. The red beds spread inland from coastal regions, tracking the expansion of oxidizing conditions across the landscape. In humid climates with abundant rainfall, oxidative weathering is most intense. The water carries more oxygen, penetrates deeper into soils, leaches iron from minerals, and reprecipitates it as oxides. In arid climates, the process is slower but still operative, with episodic rains and evaporative concentration creating conditions favorable for iron oxide formation. The red beds become a global phenomenon, appearing on every continent, in diverse climatic settings. Wherever oxygen and iron-bearing rocks coexist, the color of Earth's land surface is changing. From space, if anyone were there to look, which no one is, the continents would appear subtly different than they did in the Archean. The bare rock still dominates, gray and brown and tan, but now there are hints of red. Patches where oxidative weathering has stained the surface, regions where river systems carry red sediment to their deltas. The transformation is gradual, taking place over millions of years, but it is directional. The continents are rusting, and the rust is accumulating in forms that will persist for billions of years, surviving erosion and burial and metamorphism to tell their story to future geologists. The red beds contain clues about atmospheric oxygen levels, the intensity of oxidation, how thoroughly the iron is converted from reduced to oxidized states, provides a rough proxy for oxygen concentrations. Completely red sediments suggest abundant oxygen, enough to oxidize all available iron. Mottled sediments, with patches of red and gray, suggest lower oxygen levels or fluctuating redox conditions. Gray sediments, with only minor red staining, suggest oxygen is present but scarce, barely sufficient to oxidize exposed surfaces. By mapping these variations across time and space, researchers can track how oxygen concentrations evolved during the Paleoproterozoic. The mystery that emerges from this mapping is the patchiness. Not all regions show red beds at the same time. Some areas develop red bed sequences early, during the initial phase of the Great Oxygenation Event, while others show red beds much later, hundreds of millions of years after oxygen first rose. This could reflect local environmental conditions. Perhaps some regions were more humid, or had different rock types, or experienced different weathering rates. Or it could reflect genuine spatial variation in atmospheric oxygen, with some regions receiving oxygen-rich air masses and others remaining relatively reducing. Disentangling these possibilities requires careful sedimentological and geochemical analysis of multiple sections from different paleocontinental settings. What is clear is that oxidative weathering, once established, becomes a major component of the rock cycle. The weathering of continental rocks consumes oxygen. Each iron atom oxidized removes oxygen from the atmosphere, but it also produces oxidized sediments that are relatively stable against further weathering. The red beds, once formed, resist additional oxidation because the iron is already in its highest oxidation state. They become a stable reservoir, locking away oxidized iron for geological timescales. This represents a long-term sink for iron and a transformation of the continental surface that is essentially irreversible without burial and reduction. The soils developing on these oxidized surfaces are different from Archean soils. They are richer in iron oxides, poorer in reduced minerals, more acidic in some cases due to the oxidation of sulfides to sulfuric acid. These new soil chemistries affect mineral weathering rates, nutrient availability, and the fate of other elements. Phosphorus, for example, binds strongly to iron oxides, potentially becoming less available for biological uptake. Trace metals like copper and zinc may be mobilized or immobilized depending on redox conditions. The entire geochemical cycling of elements at Earth's surface is being reorganized in response to the presence of atmospheric oxygen. The red beds continue to accumulate through the Paleoproterozoic and beyond. They become one of the dominant sedimentary rock types in the Proterozoic, filling sedimentary basins, mantling floodplains, recording the progressive oxidation of the continents. Some of these formations will be spectacularly preserved, the red sandstones of the American Southwest, for example, though those are much younger, still owe their color to the same basic process. Iron plus oxygen equals rust. The Paleoproterozoic red beds are older, often more metamorphosed, but the color persists. Hematite is stable across a wide range of metamorphic conditions, and even rocks that have been buried and heated retain their red tint, a memory of the oxidizing conditions under which they formed. The continents rust, the oxygen rises, and the surface of the Earth, for the first time in its history, begins to glow red in the low-angle light of sunrise and sunset, reflecting wavelengths that were absorbed before, announcing to no one the chemical revolution that has transformed rock and sky and sea alike. The rust blooms, spreads, settles into the landscape, and waits, patient as stone, permanent as geology, for the next transformation to come. The ozone begins to form in silence, molecule by molecule. In the upper atmosphere where ultraviolet radiation is most intense, the chemistry is simple. An oxygen molecule absorbs a UV photon and splits into two oxygen atoms. Each oxygen atom then collides with another oxygen molecule, forming ozone, O3, a bent molecule with 3 oxygen atoms instead of 2. The ozone itself absorbs UV light, particularly the wavelengths that are most damaging to DNA and proteins. In absorbing this light, ozone protects the surface below, creating a shield that will eventually allow life to colonize land. But that is still over 1 billion years in the future. For now, the ozone layer is just beginning to form, a trace presence in the stratosphere. The formation requires a minimum oxygen concentration, below about 1% of present atmospheric levels, roughly the same threshold that makes aerobic respiration viable. There isn't enough oxygen to produce a meaningful ozone layer. The oxygen molecules are too scarce, the collisions too infrequent. Above this threshold, ozone production accelerates, and a persistent layer can develop in the stratosphere, roughly 15 to 30 kilometers above the surface. The Great Oxygenation Event brings atmospheric oxygen across this threshold, probably for the first time in Earth's history. The ozone layer begins to form, thin and patchy initially, but present. The effect on surface UV levels would be gradual and difficult to detect without instruments that won't be invented for billions of years. Ultraviolet radiation has been flooding Earth's surface since its formation, breaking apart organic molecules, limiting the environments where life can survive. The earliest life evolves in water, which provides natural UV shielding. Even a few meters of depth is sufficient to block most damaging wavelengths. The stromatolites that have built themselves for billions of years do so in shallow water. But not too shallow. The very surface layers, exposed to full UV at low tide, are typically dead, with living bacteria residing slightly deeper where water or sediment provides protection. Only took 4 billion years to develop sunscreen, and nobody notices. The ozone accumulates without announcement, without visible change in the sky or sudden expansion of habitable zones. The UV flux at the surface decreases incrementally, year by year. As the ozone layer thickens, the change is too slow to affect any individual organism, but over evolutionary time, it opens new possibilities. Organisms that can tolerate slightly higher UV doses gain access to shallower water, to intertidal zones, eventually to subaerial environments. The ozone layer is creating real estate, expanding the portion of Earth's surface where life can exist. The layer itself is dynamic, constantly being created and destroyed. Ozone forms when UV hits oxygen, But ozone also breaks down when it absorbs UV or when it encounters other atmospheric gases. The balance between production and destruction determines the steady-state concentration. In the Paleoproterozoic, with oxygen concentration still far below modern levels, the ozone layer is probably thin by contemporary standards, perhaps 10 to 20% as thick as the modern ozone layer. But even a thin ozone layer provides significant protection. UV attenuation is logarithmic. Each additional bit of ozone blocks a disproportionate amount of radiation. The formation of the ozone layer represents a feedback in the oxygen cycle. Ozone protects surface life from UV damage, which could potentially increase biological productivity and thus oxygen production. But ozone formation also consumes oxygen. Each 3 molecules of O2 converted to 2 molecules of O3 removes oxygen from the lower atmosphere, temporarily at least. When ozone breaks down, it releases oxygen again, so the net effect is neutral on long time scales. But on shorter time scales, ozone formation acts as a buffer, smoothing out fluctuations in lower atmospheric oxygen by sequestering it in the stratosphere. The scientific challenge in reconstructing the early ozone layer is the lack of direct proxies. We have no ozonometer in ancient rocks, no mineral that forms only in the presence of stratospheric ozone. What we have are indirect inferences based on atmospheric oxygen levels, which we estimate from other proxies like red beds, uranium mobility, and sulfur isotope signatures. From oxygen estimates, we can model ozone production using photochemical calculations. But the models require assumptions about atmospheric structure, temperature profiles, and the abundance of other trace gases. Different models yield different estimates for early ozone concentrations, ranging from negligible to perhaps a quarter of modern values. What is certain is that the ozone layer, once formed, becomes a permanent feature of Earth's atmosphere as long as oxygen concentrations remain above the threshold. The layer will vary in thickness over geological time as oxygen concentrations wax and wane. But it will not disappear entirely. It represents a new kind of atmospheric structure, a stratified chemistry where oxygen is preferentially destroyed in the upper atmosphere to protect molecules at the surface. It is an accidental shield, a byproduct of photochemistry, and it will enable the eventual colonization of land by complex life. The UV radiation continues to pour down, as it always has, but now it encounters a gauntlet. First, the ozone layer in the stratosphere, absorbing the shortest and most energetic wavelengths. Then the remaining UV reaches the surface, where water, rock, and biological pigments provide additional protection. The total flux at the surface is lower than it was in the Archean, and will continue to decrease as the ozone layer thickens over the coming hundreds of millions of years. The surface is becoming safer, incrementally, in ways that no organism alive can perceive, but that evolution will eventually exploit. The ozone molecules drift in the stratosphere, colliding with each other, with oxygen, with nitrogen molecules that make up most of the atmosphere. They absorb UV photons and break apart, reform, break apart again in a continuous cycle of creation and destruction. The layer has no sharp boundary. It is simply a region where ozone concentrations are higher than elsewhere, a diffuse zone of elevated O3 mixing ratios. From the surface, it is invisible. From space, if viewed in the right wavelengths, it would appear as a faint absorption feature in Earth's spectrum, a signature that this planet has oxygen in its atmosphere and processes that create ozone. The layer forms quietly. It thickens gradually, and far below, in the oceans and on the rusting continents, life continues its slow evolution, unaware that the sky has gained a shield, that the cosmos is being held at bay by 3 atoms of oxygen bound together in an unstable configuration, that the future colonization of land is being made possible by chemistry happening too high and too subtly to be noticed. The ozone accumulates, the UV flux decreases, and the surface of Earth, for the first time since its formation, begins to approach conditions where exposed life might someday thrive. The complex cells emerge from the darkness, though not literally. Many evolve in sunlit waters, in the productive zones where energy is abundant and oxygen is available, but they emerge from conceptual darkness, from the long Archean and early Proterozoic eras when cellular complexity remained minimal, when life consisted almost entirely of simple prokaryotic cells without internal compartments or elaborate structures. These new cells are different. They are larger, often 10 to 100 times the volume of bacteria. They contain internal membranes that divide the cell into compartments, a nucleus housing the genetic material, mitochondria producing ATP, eventually chloroplasts in some lineages capturing light. These are eukaryotes, and their appearance represents one of the most significant evolutionary transitions in the history of life. The timing of eukaryotic origin is debated, with estimates ranging from about 2.7 billion to 1.6 billion years ago, depending on which evidence is weighted most heavily. Molecular clock studies, which compare genetic sequences across modern eukaryotes to estimate when lineages diverged, generally favor earlier dates, perhaps 2.3 to 2.1 billion years ago, coinciding with the Great Oxygenation Event. Fossil evidence, which requires finding preserved cells with recognizable eukaryotic features, suggests later dates. The earliest widely accepted eukaryotic fossils are around 1.6 to 1.8 billion years old. The discrepancy may reflect the difficulty of fossilizing soft-bodied, single-celled organisms, or it may indicate a long period between the origin of eukaryotes and their becoming abundant enough to show up commonly in the fossil record. What is clear is that eukaryotes require oxygen, not absolute dependence in all cases. Some modern eukaryotes can survive in low oxygen or even anoxic environments, but the ancestral eukaryote, the first one, almost certainly needed oxygen for its mitochondria to function. Mitochondria are the powerhouses of eukaryotic cells, organelles that use oxygen to produce ATP via aerobic respiration. They are also, according to endosymbiotic theory, derived from free-living bacteria that were engulfed by a host cell and became permanent residents. This engulfment event, whenever it occurred, required that both the host and the engulfed bacterium could tolerate or use oxygen. The Great Oxygenation Event creates the environmental conditions necessary for this to happen. Only took 2 billion years to invent the eukaryotic cell, and most of that time was spent not inventing it. The Archean, despite its length, over 1.5 billion years, produces no confirmed eukaryotes. The cellular architecture remains stubbornly prokaryotic, simple, small. Then oxygen rises, and within a few 100 million years, brief by geological standards, eukaryotes appear. The correlation is suggestive. Oxygen doesn't just make aerobic respiration possible, it makes the energetic demands of a large, complex cell manageable. A eukaryotic cell requires vastly more energy per unit volume than a prokaryotic cell, and that energy comes from mitochondria running aerobic respiration. The early eukaryotes probably live in oxygen-rich pockets, the shallow tropical seas where cyanobacterial productivity is highest. The oxygenated surface layers above anoxic depths, perhaps even the sub-ice environments where oxygen has accumulated in isolation. These are the zones where oxygen is reliably available, where the investment in mitochondria and the metabolic machinery to use oxygen pays off. The eukaryotes are probably not abundant initially. They are likely rare components of microbial communities, outnumbered by bacteria and archaea that continue to dominate most environments. But they are present, evolving, diversifying into lineages that will eventually give rise to all complex multicellular life. The fossil record from this era preserves occasional large cells, sometimes with organic walls showing evidence of complex internal structure. These fossils are often compressed, flattened by the weight of overlying sediments, making detailed morphology difficult to interpret. But their size alone is telling. Cells larger than 20 micrometers in diameter are almost certainly eukaryotic, because prokaryotic cells are constrained by diffusion limits to remain small. The appearance of such large cells in rocks from around 1.8 to 1.6 billion years ago is taken as strong evidence that eukaryotes had evolved and become at least occasionally abundant by that time. The genetic complexity of eukaryotes is staggering compared to prokaryotes. Eukaryotic genomes are larger, containing more genes, more non-coding DNA, more regulatory machinery. The nucleus itself is an innovation, a double membrane that separates transcription from translation, allowing for more sophisticated control of gene expression. The cytoskeleton, a network of protein filaments that gives eukaryotic cells their shape and allows internal transport, is far more elaborate than anything in prokaryotes. These innovations don't appear all at once. They evolve gradually, one feature at a time, over hundreds of millions of years, but they are enabled by the energy surplus that aerobic respiration provides. The mystery that remains is the nature of the host cell that engulfed the proto-mitochondrion. Was it a bacterium or an archaeon? Recent genetic evidence suggests the host was probably related to archaea, specifically to a group called the Asgard archaea that possess some eukaryote-like features. The engulfed cell was almost certainly a bacterium, likely related to modern alpha proteobacteria. But the exact circumstances of the engulfment, was it predation, parasitism, or some form of symbiosis from the start, remain unknown. The fossil record cannot resolve these questions. We have only the outcome, a chimeric cell combining features of both archaea and bacteria, creating a new domain of life. The eukaryotes begin to diversify. By 1.5 billion years ago, multiple lineages are recognizable in the fossil record: possible algae, probable protozoa, organisms with complex life cycles. The diversification will continue for billions of years, eventually producing the staggering variety of eukaryotic life visible in the modern world: plants, animals, fungi, and countless single-celled protists. But it begins here, in the Paleoproterozoic, in the oxygen-rich waters created by cyanobacterial metabolism and preserved through the depletion of the ocean's iron buffer. The eukaryotes are the children of the Great Oxygenation Event, organisms that could not exist without the oxygen that cyanobacteria produced and that aerobic bacteria learned to use. The deep ocean remains largely anaerobic, largely prokaryotic. The eukaryotes are confined to the surface and shallows, to the zones where oxygen is present. This two-tiered ocean structure, oxygenated surface, anoxic depths, will persist for hundreds of millions of years. Eventually, ocean circulation will bring oxygen to the depths, fully oxygenating the oceans and creating conditions where eukaryotes can occupy the entire water column. But that full oxygenation is still far in the future. For now, the eukaryotes wait in the shallows, evolving, complexifying, preparing for a future they cannot anticipate. The cells continue to divide, to mutate, to explore evolutionary space. The oxygen continues to accumulate, stabilizing at concentrations still well below modern levels, but sufficient to support aerobic life. And in those oxygen-rich pockets, in the warm, shallow seas and cold sub-ice lakes, the eukaryotes continue their patient work of becoming complex, of assembling the cellular machinery that will eventually build forests and coral reefs and the bodies of animals that will walk on land. The foundation is laid, the threshold is crossed, and in the deep, cellular darkness, life waits for its next transformation. The long exhale settles into something approaching equilibrium, Oxygen concentrations in the atmosphere stabilize at levels estimated between 1 and 10% of modern values, perhaps 1 to 2% of the atmosphere by volume. Enough to support aerobic respiration, enough to create a thin ozone layer, enough to rust the continents, but far below the 21% that will characterize the Phanerozoic world. This plateau will persist for over 1 billion years, through most of the Proterozoic eon, a period sometimes called the boring billion by geologists for its apparent chemical and biological stasis. But the stasis is relative. Evolution continues. The eukaryotes diversify. The oceans and atmosphere maintain their new oxygen-enriched state. The planet has found a new equilibrium. The Great Oxygenation Event, if it can still be called an event at this point, transitions from active crisis to steady state. The cyanobacteria continue producing oxygen. But now that production is balanced by consumption, aerobic respiration by bacteria and eukaryotes, oxidative weathering of rocks, reaction with volcanic gases, the balance is not perfect. There are fluctuations, periods when production exceeds consumption and oxygen rises slightly, periods when consumption exceeds production and oxygen falls. But the net trend is flat. The system has reached a quasi-stable state that will persist until new factors emerge to disrupt it. The ice retreats. The Huronian glaciation, which has persisted on and off for 300 million years, finally ends as carbon dioxide from volcanic outgassing accumulates in the atmosphere, rebuilding a greenhouse effect sufficient to warm the planet. The oxygen-methane chemistry that drove the initial cooling is no longer relevant. The methane is gone, destroyed by oxygen, and will not return to high concentrations. Carbon dioxide becomes the primary greenhouse gas, as it will remain for most of Earth's subsequent history. The glaciers melt, the sea level rises, the coastlines shift, and the stromatolites, released from their ice-bound refugia, expand back into the shallow seas. Only took the planet 300 million years to recover from its own oxidation, and the recovery is incomplete. Earth never returns to the warm Archean climate. The orange sky is gone permanently, replaced by a pale blue atmosphere that will gradually deepen in color as oxygen concentrations increase over the next billion years. The continents remain red in places, stained by iron oxides that won't erode away. The deep ocean remains largely anoxic, stratified between oxygenated surface waters and anoxic depths. The transformation is permanent. Earth has become an oxygenated planet, and it will remain so for the rest of its habitable lifetime. The biological consequences of oxygenation will take another billion years to fully manifest. The eukaryotes diversify slowly, experimenting with different cellular architectures, different metabolic strategies, different life cycles. True multicellularity, organisms composed of many cells working together, with specialized cell types and complex body plans, won't evolve until around 600 million years ago, almost 2 billion years after the Great Oxygenation Event. The delay is puzzling. Why does it take so long for life to exploit the energetic possibilities that oxygen provides? The answer is probably multifactorial. Low oxygen concentrations limiting what's possible. Ecological competition preventing radical innovations. Genetic constraints requiring long periods of evolution to overcome. But the delay is real, recorded in the fossil record's long stretch of microbial dominance. The ocean chemistry stabilizes into a pattern that will persist through the mid-Proterozoic. The surface waters are oxygenated, supporting aerobic life. The deep waters are anoxic, often sulfidic, supporting anaerobic metabolisms. In between, at the boundary between these two zones, complex chemical gradients develop where multiple metabolic strategies can coexist. These boundary zones may be hotspots of evolution, places where the availability of both oxygen and reduced compounds creates diverse ecological niches. But the evidence is indirect, inferred from geochemistry rather than observed directly in fossils. The continents continue to weather. The rivers continue to carry dissolved iron, sulfate, and other products of oxidative weathering to the seas. The banded iron formations stop forming. The ocean's dissolved iron is finally depleted to the point where massive precipitation no longer occurs. Later, iron formations will exist, but they are smaller, more localized, formed under different conditions. The great era of banded iron deposition, which spanned perhaps 600 million years, is over. The rocks it produced will remain, some of the oldest and most extensive sedimentary formations on Earth, monuments to the rusting of an ocean. The cyanobacteria persist. They continue building stromatolites, continue photosynthesizing, continue producing oxygen that is now used as much as it accumulates. They are no longer terraforming the planet, that work is done, but they are maintaining it, sustaining the oxygen concentrations that make aerobic life possible. In a sense, they have created the world that all subsequent complex life will inhabit. Without cyanobacteria and the great oxygenation event, Earth would be a microbial planet indefinitely, dominated by prokaryotes operating anaerobic metabolisms, with no possibility of animals or plants or any of the macroscopic organisms that will eventually cover the planet. The scientific legacy of the great oxygenation event is still being written. New proxies are developed, new isotopic systems explored, new rocks discovered and analyzed. Each study refines our understanding of the timing, the mechanisms, the global extent of oxygenation. But many questions remain open. How exactly did oxygen concentrations rise, gradually or in pulses? How did life adapt to the presence of oxygen, through gradual evolution or through rapid selection in crisis conditions? How heterogeneous was oxygenation? Did different ocean basins oxygenate at different times, or was it a globally synchronous event? The rocks preserve answers, but they require patient interrogation. What is beyond doubt is that the great oxygenation event represents one of the most profound transformations in Earth's history. It rivals the origin of life itself in significance, because it creates the conditions necessary for complex life. Without oxygen, there are no animals, no plants, no fungi, no possibility of human observers looking back across billions of years to study the event that made their existence possible. The event is a boundary, a threshold, a point of no return. Earth before the great oxygenation event is a fundamentally different planet than Earth after. The chemistry, the biology, the possibilities, all are transformed. The oxygen continues to cycle, produced by photosynthesis, consumed by respiration and weathering, maintained at concentrations that represent a balance between sources and sinks. The balance will shift over geological time, with oxygen rising to higher concentrations in the late Proterozoic and again in the Paleozoic, reaching modern levels only in the last few 100 million years. But the foundation is set here, in the Paleo-Proterozoic, when oxygen first rises and the planet learns to breathe. The long exhale is complete, the transformation is finished. And in the oxygenated waters, in the rusted continents, in the thin ozone layer above, the future is beginning to take shape, though it will be over 1 billion years before that future includes anything we would recognize as complex life. The great oxygenation event ends not with drama, but with equilibrium, not with resolution, but with continuation. The oxygen rises, stabilizes, and waits, patient as geology, inevitable as chemistry, for what comes next. The stillness now is different from the stillness before. It is the stillness of a planet that has passed through transformation and arrived somewhere new. Somewhere it will remain for eons. The cyanobacteria photosynthesize in their quiet rhythms. The stromatolites grow their millimeters per year. The oxygen cycles between production and consumption in a balance that has become almost stable. The crisis, if it ever felt like a crisis to organisms without foresight, is over. What remains is maintenance, continuation. The patient work of sustaining a planet that has learned to carry oxygen in its atmosphere and water. The oceans move in their slow circulations, carrying warmth and cold, oxygen and nutrients, connecting the surface to the depths in cycles that operate on time scales of centuries. The continents weather grain by grain, their surfaces rusting under skies that are no longer orange but not yet the deep blue of modern Earth. The ice has retreated to the poles, leaving behind only the tillites and striations that record its former presence. The world is warming again, returning to temperatures more hospitable to life. Though it will never return to the Archean warmth, that era is gone, irretrievable, locked in the past by chemistry that cannot be undone. In the oxygenated shallows, the eukaryotes continue their slow diversification, invisible to any eye that might observe but present in the genetic and chemical record that future researchers will one day decode. The oxygen they breathe is a gift and a burden, enabling complexity but demanding constant defense against its corrosive nature. They persist, they evolve, they wait, unknowing, for the deep future when their descendants will build bodies of many cells, will colonize every corner of the planet, will eventually develop consciousness and language and the ability to look back and wonder how it all began. The sky darkens towards sleep, not night, but the geological sleep of a planet settling into new rhythms after long change. The oxygen will rise again someday, in another billion years, reaching concentrations that permit giant insects and massive forests. But that is far ahead, beyond imagination. For now, there is only the present, the oxygen cycling, the bacteria photosynthesizing, the slow erosion of mountains and the slower deposition of sediments on seafloors. The planet has been oxygenated, the event is complete, and in the quiet that follows transformation, in the pause between what was and what will be, Earth rests. The stromatolites continue their ancient work, the oxygen continues its cycle, and somewhere in the deep chemistry of cells, in the patient exploration of evolutionary space, the seeds of future complexity are being sown, awaiting their moment across billions of sunrises yet to come. Sleep finds the planet. Equilibrium holds, and the great oxygenation, having remade the world, becomes simply the way things are. Background, foundation, the chemical bedrock on which all future life will build.